So hello, welcome and thank you all for taking the time to join us for today's Prism Sound Wednesday webinar. Today is actually part two of a two-part series looking at audio converter measurements. Part one, we looked at D to A converters, and in today's session we're going to be looking at A to D converters for audio. And we're going to be taking a look at making some measurements on these types of audio devices. I am your presenter today. My name is Simon Woolard and I'm an applications engineer here at Prism Sound headquarters in the UK. And Prism Sound, for those of you who are perhaps less familiar with the company, we are a manufacturer of a range of high-end digital audio and analog audio solutions. And in particular, we make a range of audio measurement solutions, and I work directly in the department at Prism Sound dealing with our audio test and measurement clients, helping to solve their measurement problems and bringing them up to speed on how to use our solutions. So before we get stuck into the agenda and before I start taking you through some of the background theory that I want to talk through, I'd like to just ask you, the audience, a question. And in order to do that, I'm going to jump straight into an audio measurement here. I have an analog to digital converter hooked up to my measurement system. We're looking at the software that allows us to control the measurement system's generator functions and to display the analysis results. And right now you can see that I have a digital signal with a frame rate of 48 kilohertz, and on my trace window here you can see that I have a time domain signal in green and some FFTs of channel A and B in blue and red respectively. Now you may notice that the y-axis of these traces, both time domain and frequency domain, is currently shown in units of dBFS, and I also have some signal amplitude readings down here at the bottom left hand corner, again in units of dBFS. Now I'm going to ask you a question by means of a NetViewer survey, and you will see in just a second a survey pop up on your screen if you are using a PC rather than a Mac to join in today's presentation. And the question I would like to ask you, and there are multiple possible answers, is where can units of dBFS be used in audio measurements? And I'd like you to consider all of the possible answers and let me know all of the responses that you think are valid. In other words, where can we use units of dBFS in audio measurements? And your options are, for those of you that perhaps are joining in on a Mac, for analog generator amplitudes, analog analyzer amplitudes, digital generator amplitudes, digital analyzer amplitudes, distortion measurements, noise measurements, or perhaps none of the above. So I'd like you to take a look at those possible answers, select all the ones that you think are correct, and send those responses in to me. And I'll be treating your responses as confidential. We'll take a look at the statistics, but we won't be identifying any individual responses. So please answer those as honestly as you can. And in just a moment or two, we will take a look at how you have responded. So I'll give that survey just a few more seconds for you to consider and complete, and I will now bring it to a close. Okay, so let's look at how you have responded. And we've had a reasonable number of responses there, and actually the point that I was hoping to illustrate with this particular survey is that all of the above are audio measurements where we could use units of dBFS. So dBFS units are valid for generator amplitudes, for analyzer amplitudes in both the analog and digital domains, and we can also, if we want to, measure things like distortion and noise and any other parameter that we like in units of dBFS. I should say in situations where an absolute measurement unit has been specified. So, this will bring me on to something that I want to talk about in a bit more detail a little later on, something called a DA lineup, which defines the relationship between our analog full scale and digital full scale in the device that we're testing. And it's going to be important to understand and use that DA lineup correctly in order to be able to use units of dBFS in both the analog and the digital domains. So more on that later. For now, I'm going to take you back into my slides and just run you through the agenda for today's presentation. So firstly then, I want to talk briefly about some design issues in relation to audio analog to digital converters. This is not a tutorial in designing converters, but we need to consider a few things that are relevant at the design stage in order to understand what we want to measure and why. So that will bring us nicely on to considering what kind of tests to run on our analog to digital converters. And then I'm going to take you through a series of live measurement demonstrations, all on analog to digital converters, but we're going to consider a number of different interfaces on which to measure our digital signal. So first of all, I'm going to look at measuring the performance on AES EBU interfaces from our converter outputs. I'm then going to take a look at measuring the serial digital interface outputs of our converters. And then finally, we're going to consider making some measurements on converters that have a PC audio interface. Okay, so let's start at the beginning then and talk about some design related issues. Now, some of you may know Ian Dennis, our technical director here at Prism Sound. He has many years of experience in both designing A to D and D to A converters and also in designing test equipment for evaluating their performance. And Ian recently presented a paper at an Audio Engineering Society conference considering in particular the challenges in designing modern audio converters, and I've taken some of his content and adapted it for the purposes of this discussion here. Now, as Ian outlined, transparency is one of the key considerations in most audio applications when we're designing converters. It's fair to say that in most situations what we want to do is try and prevent our converter design from modifying our original signal or introducing any artifacts that were not present originally. As I say, that's fair to say for the majority of converter-based applications. Preserving transparency is what it's all about. So in considering where our design could potentially go wrong, Ian put together this schematic outlining a typical A to D converter system. And that's actually a relatively complex system, as you'll see from the diagram on your screens. So where in this system can things potentially go wrong? Well, here's the list of things. We could have the data converter device itself, the clocking reference that's supplied to the device, the voltage reference that's supplied to the converter device, the power supply that powers the whole system up, the interfaces that might exist between the converter and the host PC, analog circuitry, and digital parts. Now, when we're trying to understand the performance and behavior of something like an analog to digital converter with such a complex architecture as this, we can use our ears. They're very useful analytical tools to tell us something about how the device is performing and how it sounds. But in order to really get down to the microscopic levels of detail that we need as design engineers to be able to figure out exactly where the design is going wrong if something's not quite working properly and perhaps not sounding right, we will need some fairly sophisticated analytical measurement tools in order to help us understand the system. And that will be the focus of today's presentation. We'll be using those analytical tools to get to the bottom of design-related issues in our A to D converters. So let's consider this list then of the areas where our design could potentially go wrong. And let's look at the data converter device itself. Now, I've done a quick Google search and found a number of off-the-shelf parts available from leading manufacturers of semiconductors, most of whom, if not all of whom, I'm sure you'll be familiar with. I'm not intending to single out any of them in particular, but my point is that it's very easy to find off-the-shelf silicon that is capable of potentially giving you a signal-to-noise ratio in excess of 120 dB and total harmonic distortion below minus 110 dB. So this is pretty good performance for pretty much any application that you're ever likely to encounter. So my point here is that it's really not very difficult to find off-the-shelf silicon that will do a fantastic job of preserving transparency and giving you a very clean recording of your analog signal. So in actual fact, the challenge in most situations certainly in today's context, is actually to achieve the potential of the data converter device that you're using in your design. So to simplify things then, I'm going to strike one of these things off my list and say the data converter is sorted, and actually our challenge is to take care of the remaining parts of our converter system to ensure that we reach the potential of our data converter device for the most discerning applications. And I'm going to talk you through a few of the issues, a few of the major issues that we might need to consider at the design stage. So let's just stop and think about, well, what is the role of the A to D converter? And in simple terms, it's a question of how much and when. So in other words, our A to D converter needs to sample and quantize our analog signal. So at very specific, discrete points in time, we want to quantize our signal to put a digitally encoded amplitude on our signal at those points in time. Now, any errors, either in our timing reference or in our amplitude reference at the converter device, will lead to distortion, and that's obviously one of the things that we want to try and prevent if we're interested in preserving the original signal, ensuring our design is transparent. So we conclude that a high-performance A to D or D to A converter really needs a very highly stable amplitude and timing reference in order to give us a faithful reproduction of the original audio signal that we were encoding. And this leads us on to considering one of the important factors in our converter design, and that is the amplitude reference. Now, I've taken a part arbitrarily from a manufacturer's datasheet here and shown you two of the pins on this device that are the points where a voltage reference needs to be applied via an external circuit. And effectively, this voltage reference determines the output level of the converter. And any noise on that reference voltage pin will intermodulate with the audio signal and give us distortion components that weren't present in the original audio waveform. The other side of this how much and when question then, the clocking, well, it's widely understood that sampling jitter at the conversion process will introduce intermodulation distortion. And a quick diagram for those of you who perhaps are a bit less familiar with this, I've shown an analog waveform here in blue with a digital clock with a series of pulses in black, and one of those pulses, the one in red, has been offset slightly from its ideal position. So I've introduced some jitter in this diagram. So I'm now going to sample this signal, quantize it to give me some digital amplitudes, and the issue here is that when we replay this digitized waveform with a system that has a clean clock free from jitter, because we've sampled at the wrong time, we've actually introduced an error in amplitude. So this illustrates how jitter, sampling jitter at the converter itself, will introduce intermodulation distortion. So in other words, our converter needs a very stable internal frequency reference. And if it's designed to synchronize to external references, as many converters are in the fields of pro audio and broadcast, as a couple of examples, then potentially we also need to be concerned about the converter's ability to recover a clock from an external source, which may be noisy, jittery. We need a good phase lock loop circuit that's able to attenuate jitter from the external reference. A couple of other issues then. Well, let's look at the power supply. It's reasonably well understood that if we're not careful with our power supply design or our local decoupling from the power supply, we may either directly introduce mains related components into the audio signal, or perhaps we might get some kind of modulation artifact, power supply modulation occurring at either the mains frequency or harmonics thereof. For switch mode power supplies, of course, running at much higher frequencies than mains, much higher than audio frequencies, we may see other intermodulation artifacts, noise and interference products appearing in band. And here's just a quick example of an FFT of a device that has a power supply related problem, and we can see here that there are a number of harmonics clearly visible in the spectrum at the 50 Hz mains frequency and its harmonics. Now, we've introduced several things already jitter, voltage reference noise, power supply related issues, which can potentially cause intermodulation distortion. And when we're looking at the A to D converter in question, we may wish to gain some insight into where those modulation sidebands are coming from. And one of the key things that we can do is actually identify whether the sidebands are being produced by some kind of jitter-related problem, or whether they're being produced by some other form of amplitude or frequency modulation. And why are we so concerned with these intermodulation sidebands? Well, they have no harmonic relationship to the original signal. And I have a quick diagram here to illustrate this. I have a diagram here showing you a spectrum of an A to D converter playing a 1 kHz sine wave. So there's our 1 kHz tone. If I were to introduce a 100 Hz modulation signal, then what we would see would be sidebands 100 Hz either side of the original audio signal. So those are tone components 100 Hz away from our audio signal that weren't present in the original signal and don't line up with any of its harmonics. So they're potentially quite unpleasant to listen to, depending on the frequency at which they occur. So, as I say, we're concerned with intermodulation sidebands, and we may well be concerned with the origin of those sidebands if we see them. And it's actually relatively straightforward to determine whether a pair of intermodulation sidebands have been produced by some kind of jitter-related problem, phase modulation, or whether they have come from some kind of amplitude or frequency modulation issue. If it's a jitter problem, a phase modulation, then what we see is that the intermodulation sidebands tend to increase in level, I should say, as we increase the audio signal frequency. So in this diagram here, I have an overlay of a number of different FFT measurements of the output spectrum of an A to D converter. And I have modulated, sorry, this is a D to A converter actually, but I have modulated the input signal of that D to A converter by introducing some 100 Hz jitter. And in each of these measurements, in the different colours that you see on the trace here, I have left everything constant, so the signal, the audio signal amplitude, the jitter frequency and the jitter amplitude. The only thing I have changed is the audio signal frequency, and that has caused an increase in sideband amplitude as the audio signal frequency increases. On the other hand, the second measurement I made here, this was a device that has some amplitude modulation, but not phase modulation, not a jitter problem. And what we see here is that under the same conditions of making a number of different measurements with different signal frequencies, everything else left constant, the modulation sidebands tend to have a fixed amplitude as the audio signal frequency changes. So that's one of the important points to note when you're looking at the measurements you're making on your converter and trying to determine whether you have a jitter related problem or some other modulation problem when you see these sidebands. One other important issue that I briefly mentioned earlier is many audio converter devices today interface with a PC in some way, shape or form. So here are a number of different audio devices that feature A to D and D to A converters and transact digital audio with a host PC via some form of interface, be it Firewire, USB, PCI, or any other form of interface that can move digital audio between your audio device and your host computer. And we may want to check whether the host PC, the drivers, and the converter device are all interacting together in the expected way, or whether there are any other unintended consequences of our design that may need attention. So having introduced a number of those design-related issues now, we can now consider what might we want to do when we come to analyse our converters. And there are two main areas that we might want to consider in the most part. One is the actual performance of the device itself, how it behaves, how it sounds, and the other is any compliances with any standards that the device has been intended to interface with other equipment using. On the performance side, there is a document from the Audio Engineering Society, AES 17, and this document details test methods that are recommended for using when you're evaluating the performance of digital audio devices. On the compliance side, in particular, I'd like to draw your attention to the AES-3 standard, perhaps still the most widely used digital audio interface format for moving audio signals between different devices. And again, this is a standard from the Audio Engineering Society, and it outlines the interface requirements for the electrical carrier, the audio data format, and the metadata format too. Now, if we just take a quick look at the AES 17 recommendations, there are a number of different families of tests, and you can see here there are quite a few different tests that you might potentially want to implement on your converter devices in order to fully understand how they're behaving and picking up all of the possible design-related problems that you might encounter. And we have already an AES 17 measurement suite built into the DScope Series 3 measurement platform that we supply and support. And this is the system we're going to be using a little bit later on for our live demonstrations. I'm not really going to focus on the AES 17 test suite because I have something new to introduce to you. Those of you that know the DScope system will potentially have used the AES 17 test suite. I'm going to show you something a little different today. And on the compliance side of things, again, there are a number of areas that you might want to check. For example, looking into word length, frame rate, and frame rate deviation checks. You might want to investigate the metadata that's embedded in the AES interface. You might want to look at the actual carrier itself, looking at the carrier amplitude, the jitter amplitude, perhaps even the carrier waveform itself. And you might want to perform some checks over extended periods of time to see whether you have any intermittent glitches or dropouts that will only be detected if you run an extended test. Again, all of these tools, complete suite of test tools for analysing both sources and receivers, are built into the DScope Series 3 analog and digital measurement platform. And again, I'm not going to dwell too much on that detail because those of you familiar with the system will potentially have used some of these tools before. We've covered some of these things in past webinars. I want to, as I say, talk about something a little bit different today. And you may well be aware that Prism Sound has a long history of manufacturing very high-end reference grade D-to-A converters and A-to-D converters. So in other words, we've been designing these kind of things for quite a long time. And we've also, as I alluded to earlier, been heavily involved in designing audio measurement solutions for some time now. And it would be fair to say that we very often take a slightly more pragmatic approach to evaluating our converter performance when we're looking at iterative design changes on the bench than running through the complete suite of AES 17 tests every time we make a minor change to a circuit design. We tend to, as I say, be a little bit more pragmatic about our testing. And in Ian's paper, at the end of his paper on design-related issues in the world of A-to-D and D-to-A converters for audio, Ian also introduced a proposed measurement summary outlining some of the more critical issues, those that are easiest to potentially get wrong, some slightly less critical but important nonetheless issues that we might want to concern ourselves with, and also some other measurement issues that don't directly translate to transparency related performance aspects. And it's this measurement summary that Ian has put together that has led us to develop a brand new application for the DScope Series 3 measurement platform that I'm going to use for the remainder of today's presentation to take us through the live measurement demonstrations. And the purpose of this testing suite was to take the complexity and time out of measuring your converters. So it's been greatly streamlined. We can simply press a few buttons, select tests from drop-downs, run a test and create a report without really having to do anything to understand the underlying test methodology that is being used by this measurement application. So it greatly simplifies the process of measuring converters, and you don't have to actually set up any of the tests yourself. So as I say, this new measurement suite will run on existing DScope Series 3 measurement systems. It's very simple, straightforward to use, and it's also highly programmable. So we're delivering this in a fixed format that allows you to run a series of tests according to how we've configured them. But if you want to customize it, change the settings in the tests, add some additional tests, remove some that you don't need to use, then that can all be done. This test is highly programmable, can be modified, adapted to suit your specific needs, which is one of the things that makes it so powerful and useful. So that being said then, let's start using it. And I want to first of all talk about making some measurements on Adca D converters that have an AES EBU output. And before I do anything else, I'm going to return to this parameter, this DA lineup that I mentioned earlier, and talk about units of dBFS in both the analog and digital domains. And what I tried to explain briefly earlier is that the DA lineup is basically a reference level that defines the maximum analog signal amplitude that corresponds to digital full scale. And if you can imagine here on the left, I have an analog device that potentially could have a maximum output level over a very wide range of amplitudes. And what we're interested in knowing is, well, what amplitude in the analog domain corresponds to 0 dB full scale in the digital domain, and that defines our DA lineup. Once we have defined the DA lineup, we can then use units of dBFS for both our generator and analyzer units, regardless of whether we're working in the analog or the digital domain. And that can be a very handy shortcut to setting up signal amplitudes at, let's say, 18 dB below the maximum analog input level of your Adca D converter, as an example there. So let me just talk you through this then with a demonstration. And here is my D-Scope Series 3 measurement system, comprising a hardware interface and a software control program. And I'm going to use it to measure an off-the-shelf analog to digital converter that has balanced analog inputs and balanced digital outputs on AES EBU interface. So I will switch back over to the test system that I showed you very briefly earlier. This is the software that controls what signals the D-Scope hardware generates and also displays the analysis results. And I'm going to launch my ADC testing application here from a quick link that I've put on my user bar here. So what I need to firstly do is say to the interface here, well, actually I want a balanced analog output connected to the input of my Adca D converter, and I'm measuring a digital output using the AES3 interface. So that has now been taken care of. What I now want to do is to establish the maximum analog input level of my converter, and I can do that very easily by hitting the Find button here, and this will do potentially two things. First of all, it will ramp up and down the analog signal generator amplitude of the D-Scope measurement system to the point where we reach 0 dB full scale on our digital output of our converter. If for any reason that can't be achieved, and that does happen in some situations, we will run through a second loop looking for the point where the distortion reaches 1%, so the clipping point of our converter. And one of those two conditions will be taken as the maximum analog input level, otherwise known as the DA lineup. So if I go into my signal generator up here, switch my units to dBu, what we will find is that if I now change the signal amplitude to 11.81 dBu, there we have it. You can see that my digital signal at the output of this converter is now reading 0 dB full scale. And that means that if I go back to the generator, remember this is an analog signal that I'm generating, switch to units of dBFS, this of course is now reading 0, but it means that I can very easily go in here and say, well, I might want to test this at minus 18 dB relative to the maximum analog input level. And I can do that very easily without having to get my calculator out and figure out exactly what signal amplitude I need. So having this DA lineup is a very neat and powerful thing and allows us to very easily switch between the analog and digital domain without having to convert reference units. Okay, so having discussed that, then we can now move on to some perhaps slightly more interesting measurement demonstrations. And the next one I'm going to take you through is a total harmonic distortion measurement, mainly because that's one of the very first things that a lot of engineers will think of trying in order to evaluate how their device is performing. So if I go back, in fact I'll just take you through the setup diagram. Again, I'm using exactly the same setup, same off-the-shelf analog to digital converter measured using the same interconnections. So back to my measurement system now, and for total harmonic distortion I have a couple of tests that I could potentially load: THD versus frequency or THD versus amplitude. I actually ran both of these tests during our recent webinar on D to A converter testing, so I'm just going to focus on THD versus frequency for now, and that will allow me to spend a bit more time talking about some other tests that we didn't cover in the D to A converter webinar recently. Okay, so I've loaded my THD versus frequency test here. You can see that I've got a couple of buttons here. One takes me to the settings page that shows how the test has been configured. I've got a help page here which gives me a little bit more information on what's being tested. And if I look at the measurement setup here, basically I'm running a sweep. So I'm going to start at 10 kilohertz and finish at 20 kilohertz. The reason for that I will discuss a little later. And I'm basically going to measure THD and THD plus N, so total harmonic distortion, and total harmonic distortion plus noise at each of these different frequencies. I also have a clever little adaptive FFT script here, and what this is going to do is look at both the signal amplitude and frequency and determine whether we're using a sensible FFT size. If the amplitude gets too small, or if the frequency gets too low, we may need to use a larger FFT size. Why are we using FFTs at all, you might ask? Well, that's because I want to isolate the total harmonic distortion from the total harmonic distortion plus noise. And THD plus N is measured using this white filter here. So it's a conventional looking notch filter to remove the fundamental and analyse everything that remains, all the noise and all the distortion. Now, as a designer, we may want to understand whether the THD plus N figure is dominated by noise or by distortion. So what I can do is, at the same time, measure THD only, so total harmonic distortion. And you can't do this with a conventional notch filter. You have to use digital frequency domain analysis and use these ideal brick wall notch filters in order to isolate just the harmonic distortion energy. So I have to use an FFT to get this THD result. Hence I'm sweeping FFT based measurements, which is slower than sweeping continuous time based measurements, but we can do a lot more with these FFT derived results. So that being said, what I'm going to do is run this test, hit the button here, and what we'll see is that the frequency first of all starts high up here, and you can see the FFT trace showing us that the tone is gradually coming downwards in frequency. We can see that these filters are tracking the signal as it goes, and we're building up a picture of how the distortion behavior of this particular device varies with respect to signal frequency. Now what you'll notice is that we're getting down to low frequencies, and these filter bandwidths appear to get wider because we're looking at this on a log scale. So behind the scenes, that script that I talked about is progressively choosing larger and larger FFT sizes as we get lower and lower in frequency, and that means that we can optimize this sweep speed so it's fastest at high frequencies where we don't necessarily need this high resolution, but where we do need it, it switches into a larger FFT size for us. Okay, so the test has now executed, and if I wanted to, I could now create a test report. I could put some notes in here if I wanted to. Simon Demo 1 for the sake of argument. And I now have a test report with all those traces that I just measured, complete with documentation about the signal amplitude that we measured at, the measurement results that I've got on the trace, and a note up here about the measurement that we've done, the conditions that we measured under, and the sample rate that my A to D converter was operating at. So I just then want to return to this question of why we only swept over this range 10 kilohertz to 20 hertz. And the reason for that is apparent. If I go back to my live FFT here, let me turn off the sweep traces for a second and open up the signal generator, which I can position up here. If I change my generator frequency to 20 kilohertz, which might be the point where you might think that you'd want to start measuring these results, you see here that my tone frequency has gone up to 20 kilohertz, but all the harmonics are now outside the audible band, and it's only when we come down to, say, 10 kilohertz that this 20 kilohertz tone now appears, or sorry, the 20 kilohertz second harmonic now appears at the upper end of the accepted audible limit of 20 kilohertz. So if we're concerned with the audible distortion performance, then it's quite common to stop your total harmonic distortion measurements at 10 kilohertz, or perhaps even a shade lower, maybe 7 kilohertz, where the third harmonic is now actually out of the audible range. If you're actually concerned with measuring those non-linearities, then you could, of course, go to your settings page and start your sweep at a higher frequency. I want to draw a line under distortion measurements for now. I'm going to jump back into my PowerPoint slides here and talk you through the next measurement. And what I'll do now is measure intermodulation distortion, and I'll use exactly the same setup as I did before, but what I want to show you this time is how you can make linearity measurements, distortion measurements, using audio signals that are at high frequencies, but we can produce non-linearities, intermodulation distortion products well inside the audible range. So that might be useful if you're looking at the audible non-linearity at signal frequencies that go above 10 kilohertz. So let's load that test, IMD versus amplitude. And if I go to my settings page now, you'll see that my generator has been configured with a twin tone signal. So in other words, we're playing two sinusoidal tones at the same time, and that may potentially give rise to intermodulation artifacts in the converter device. So if I go back to my results page, then we will see that there are the two tone components in our twin tone, 19 kilohertz and 20 kilohertz, but we also get a rich spectrum of additional intermodulation products that weren't present in the generator waveform. And this is the one that we're going to measure here, the first order difference frequency at 1 kilohertz. So 20 kilohertz minus 19 kilohertz gives us a first order difference product here at 1 kilohertz. And when I run this test, what we're actually going to be doing, if I just jump back to my settings page here, is we're running a sweep over a range of different amplitudes. So we're going to plot the intermodulation distortion as a function of generator amplitude. And that test is now executing, and we're well on the way towards the end. Again, this test is using our clever adaptive FFT script, which is deliberately choosing larger FFT sizes when the distortion results reduce in amplitude to a point where they would be potentially getting close to the noise floor, and we then need to use a larger FFT size to allow us to clearly see that distortion product above the local noise floor. Okay, so that measurement has now executed, and once again I can create a test report for posterity which documents the test settings and the measurement results in a nice, neat HTML format. Okay, so let's go back to the slides now, and I'll talk you through what we're going to do next. And what I'm going to look at here is measuring the jitter performance of the converter device. And at this stage, I would like to ask you, the audience, another question. So again, those of you who are using a PC to watch this presentation will see a survey question appear on your screens now. And what I would like to ask you is how you think you would analyze the intrinsic sampling jitter performance of an audio analog to digital converter. And I've given you a few different options here. I'd like you to tell me all of the options that you think could be used to test the sampling jitter performance of an A to D converter. So I'll give you a few moments to take a look at those possible answers and to select the ones that you think are relevant before we then take a look together at how you have responded, and we'll then move on to actually making this measurement. So I'll bring that survey to a close in a couple of seconds. I'll close that survey now then, and we will look at how you have responded. Alright, so on the screen now are the results that you've provided. A couple of people thought that we can't actually analyse this. Well, the good news is that we can. The way that we go about doing it is actually to look at the FFT spectrum and employ some maths, some mathematical processing on that FFT data in order to infer the jitter that was present at the converter stage. The other answers that I gave you here, using the Prism Sound J test, that's not appropriate in this case. That is a test that's very useful, or a test signal that's very useful for looking at how digital receivers and D2A converters behave in the presence of AES interface jitter, jitter that's specific to biphase encoded interfaces. It's not something that we use for analog to digital converter measurements. And looking at the carrier jitter of the digital outputs of a converter is not necessarily a good way of probing its distortion performance. It may give us some useful insights, and in particular it might tell us whether we've got any additional interface jitter on the AES outputs. We can even look at the jitter spectrum to get a better idea of what's going on. But the test that I'm going to show you now actually gets right into the Adca D converter itself and allows us to put a number on the sampling jitter by looking at the FFT spectrum. So let me just talk you through this then. Now, going back to a paper that was presented by Prism Sound back in 1991, we did a couple of things. First of all, we calculated the maximum permissible sampling jitter to guarantee inaudible modulation sidebands in our converter designs. And I'll spare you the complete picture of how we arrived at this result. We covered that in the recent webinar on D2A converter testing for those of you that are interested in learning a bit more about how this graph was derived. But essentially what this tells you is the maximum permissible jitter amplitude as a function of jitter frequency to ensure that you don't end up with audible intermodulation distortion sidebands. And in short, we can allow greater levels of jitter at lower jitter frequencies because the intermodulation sidebands will then appear closer to the fundamental, the audio signal, and will therefore be masked to a greater degree than sidebands that occur at higher frequencies due to higher jitter frequencies. And in that same paper that I just showed to you, we also derived some maths that allowed us to calculate the implied jitter performance at the converter by looking at the output spectrum of the converter device itself. And I should stress, and I'll probably repeat this later, that you have to be absolutely certain that what you're looking at is an intermodulation sideband caused by jitter before you can use these maths or these mathematical tools in a valid way. But that being said, let's just talk about, again, how we're going to measure this. Same setup as before. I have an Adca D converter with balanced analog inputs and AES EBU digital outputs. And we're going to measure it and look at its output spectrum and calculate the implied jitter performance. So again, I'll load my inferred jitter measurement here. This will load a different test profile. And what's happening in this test is that we are using a high frequency tone, in this case half the Nyquist limit, so 12 kilohertz for my 48 kilohertz Adca D converter. And what we're going to do, if I go back to my results page, is we're going to run a high resolution averaged FFT and take a look at these intermodulation sidebands. Now we are, as I said, making the assumption that these sidebands are being caused by jitter, and I explained earlier how you can determine whether that is the case before you do this more detailed analysis. So let's assume that I've done the analysis, the basic analysis, and I've established that yes, these definitely are jitter components. They reduce in amplitude as my signal frequency is decreased, and they increase in amplitude if I increase my signal frequency. So if that's the case, then I can run this test, and what this will do is first of all engage a large FFT size and also some averaging. And I've also got this dialog that has now popped up over here, and let's say I zoom in a little bit on the tone component here at 12 kilohertz. What I can do is select a sideband here or nearby, and let's just use these cursors to scan in and out, and they've now locked onto this pair of sidebands here, either side of our 12 kilohertz tone. And this tells us that if these sidebands were produced by sampling jitter at the converter, then the jitter was at a frequency of 187.5 Hz, and the jitter amplitude was 350 picoseconds. And I can do this for all of these points on the graph here. Let's go to these particular sidebands here. So that was 375 Hz at an amplitude of 86 picoseconds, and so on. And it's perhaps the sidebands that are out further away from the tone that we may be more interested in, because of course they are potentially more audible, being further away from our audio tone and therefore less masked, or masked to a lesser degree. So, having now performed that averaged FFT, again I'm in a state where I can create a report, and that report will be compiled complete with the FFT data that you've just seen, and also the information about the inferred jitter amplitude and frequency based on these cursor positions that we've just positioned here. Alright, so at that point I'll go back to my presentation, and now I want to move on to talk about measuring A to D converter performance on the serial digital interfaces that our converter device may have. And for example, if your A to D converter output is fed directly into some kind of DSP processor, you may want to interrupt the signal path before the DSP starts to modify the signal and start to look at the behaviour of just the A to D converter device in isolation. So that's one reason why you might want to look at the serial digital outs rather than looking at some other output, AES, EBU or PC audio interface further downstream. So what am I going to do? Well, let's talk about aliasing. That's an interesting measurement to take a look at. And just a bit of background for those of you who may be slightly less familiar with the terminology here. If our analog audio signal frequency is greater than half of the sampling rate of our A to D converter, otherwise known as the Nyquist limit, then we can potentially produce a digitized version of this signal. And this is what we get. So my sampling clock is at the bottom of the screen here. My analog waveform is illustrated here in blue. If I were to sample and quantize this signal, this would be the result. The problem here is that if I replay this digitized waveform, then this is our result. We actually get a signal at the wrong pitch. It's aliased. That is our definition of aliasing. We can see from these two diagrams that we have a rather different waveform on the analog side than we do on the digital side. So aliasing is something that we need to be concerned about, and we employ an anti-alias filter to remove high-frequency signals above the Nyquist limit prior to the quantization stage. So there's our Nyquist limit, and here is a measurement of an anti-alias filter rolling off the signal down to very low amplitude before we get to the Nyquist limit. And what tends to happen in an analog to digital converter device, if we consider the analog input here in the top measurement and the digital output here in the bottom measurement, here's the Nyquist limit in my example, 24 kilohertz, so it's a 48 kilohertz converter. As the tone frequency increases towards the Nyquist limit, we get a one-to-one mapping, so the output signal corresponds exactly to the input signal frequency, as I've illustrated here. But above the Nyquist limit, it's reflected. It folds back down below the Nyquist limit, and the frequency of the tone gets lower as the input frequency gets higher. And you can see in this example the effect of the anti-aliasing filter here, that the tone amplitude is reducing as the tone wraps back down towards the audible band, ending at 20 kilohertz. So the anti-alias filter is something that we might want to characterize as part of our evaluation of the converter device. So here I have an analog to digital evaluation board. I've chosen an evaluation board because it gives me easy access to the serial data outputs. And I'm taking those serial outputs, in this case I2S format, into the serial input of this additional device that I've introduced into the measurement setup here, known as our VSIO adapter, which is simply an interface converter that takes serial inputs and outputs and converts them to and from the AES EBU format that the standard Dscope Series 3 hardware is capable of communicating over. So that's my measurement setup. Again, I'm going to switch over to the measurement system here and load my alias test. So that is here. This will load a new test for me. Again, I don't have to concern myself with how to set this up. What I do need to do is change the connections on my measurement system so that I'm measuring the right device. So just a second while I do that. Okay, so my analog to digital converter is now connected. I'm looking at the serial outputs of the device. Now I should be seeing a sine wave at 1 kHz, but quite clearly I'm just seeing noise at the moment, and the reason for that is that I need to configure my VSIO adapter to handle the data format in use by this Adca D converter reference board. And what I have down here in this little memo, I've copied and pasted the timing diagram from the manufacturer's datasheet for this converter so that you can see how the clock and data format needs to be configured on my VSIO adapter control if I want to correctly interpret the data. So first thing you'll notice is that the word clock here is inverted and it's firing early, 1 bit clock cycle ahead of the most significant bit. So go to my word clock, I need to invert it, make it fire early, and you now see that this timing here in the VSIO control reflects the word clock format of the device under test. And I need to do the same with the bit clock. That needs to be inverted. You'll see that now matches the format on the timing diagram. And the data is configured as most significant bit first, so I need to uncheck that box there. And now you'll see that in my small trace window here in the top right hand corner of the screen, we've got something that looks like it could well be a sine wave. So back to my results page, slightly bigger trace window, and yes, we can see that there is a sine wave now present on the trace window. Okay, so we're ready to perform our measurement. If I look at my settings, what we're doing here is varying the analog generator frequency over a range starting at 18 kHz and ending at 47 kHz, which will take us right through that range of frequencies, starting just below the Nyquist limit of, in this case, 24 kHz, and ending up well above that Nyquist limit. So, if I run my test now, I will explain the results that we're measuring, because we're actually measuring two different results on both channels here. Now, the first result is the output of this blue measurement filter. So this is looking at the FFT data, tracking the analog generator frequency and applying a narrow band filter. So we're just measuring the signal centered around this filter frequency here. Now, this particular sweep has been set up in quite a smart fashion, and there's a script running at each of these sweep steps, and that script is looking at the Adca D converter's digital output frame rate, looking at the signal generator frequency and saying, well, hang on, we've now gone above the Nyquist limit, we're at 26 kHz now, so this filter starts to track back downwards towards the upper limit of 20 kHz that we normally consider to be the limit of human hearing. So this filter is now tracking our alias component that you can see here in our FFT response, and the result is being plotted in blue here. So this is in effect the response of the anti-alias filter of our Adca D converter. But we have another result here in pink, and the pink result is basically produced by the measurement filter here in white. And this is just simply a low-pass filter rolling off at 20 kilohertz, the normally accepted upper limit of human hearing. So we're plotting two different things. The blue trace here shows us the amplitude of the signal and then the alias component, so it shows us effectively the response of the anti-alias filter, whereas the pink trace shows us an approximation of the audibility of the resulting alias products. So you can see that you get quite a difference between these two different curves here. And that trace is almost complete now. The measurement is just coming to a close, and having finished the measurement now, we can again create our report showing both of those traces, the anti-alias filter response and also the audibility of the alias products, here in our test report. Okay, so moving on then, we'll look at the next measurement demonstration now, and I want to consider a crosstalk measurement. Relatively straightforward test to implement. Once again, I'm using the same setup as before, looking at the serial data outputs of my A to D converter evaluation board. And if I go back to my measurement system here and select crosstalk as my result, then what we will be able to measure here is crosstalk as a function of frequency. So once again, I'm running a sweep from 20 kilohertz to 20 hertz, again using this adaptive FFT size script here that will look at the crosstalk amplitude, look at the crosstalk frequency, and determine the most appropriate FFT size to avoid wasting time when we can get away with low resolution, but taking care to ensure that we have high resolution when we need it. So again, I'll run this test, and we'll actually go through two sweeps here. The first one, you'll see that channel B, the red FFT trace, channel B is muted, and there's only signal present on channel A, the blue trace. And when this sweep has finished executing, then we will do the same again, but in the other direction. So this time we will mute channel A and measure the crosstalk components on channel B. And that sweep is now executing the B to A crosstalk, and it is now drawing to a close. Once that is finished, again, I can go through the process of simply hitting my Create Report button here and generating my HTML formatted crosstalk measurement report. Okay, so I'd like to wind up there on serial digital interfaces for now, and consider finally making measurements on A to D converters with a PC audio interface. And as I mentioned earlier, there is a large and growing number of A to D, D to A converter devices that interface with a host PC. So digital audio data is moved over a USB or FireWire or PCI or other interface to the host PC from the device that we're interested in testing. And that presents an interesting challenge. Historically, these types of devices would be tested by perhaps generating some WAV files in some third-party software, perhaps recording what's coming in via the USB stream onto some third-party software, and doing some analysis on WAV files offline. So it's a little bit involved, time-consuming, and potentially open to error if you're not 100% confident that your digital audio editing software is doing what you think it ought to be doing. So, in the Dscope Series 3 platform that we are using for today's live measurements, we have a rather unique feature that allows us to talk directly at driver level to these types of devices that are designed to interface with a host PC. So in addition to the digital and analog inputs and outputs on the front panel of the Dscope 3 hardware, the Dscope 3 software is also able to communicate at driver level with these PC audio interface type devices. So let's consider that we had a PCI card that featured some A to D converters that took inputs to the computer, and some D to A converters that took outputs from the computer to the outside world. In the D to A case, we could address the analog outputs of this device through the device driver, so we'd route digital audio signals through the Dscope software to the device under test, and analyze its analog outputs using the Dscope Series 3 analog inputs. And likewise, in the case that I'm about to show you, we can take analog outputs from the test system, apply them to the Adca D inputs of this device, and analyse the signal that's coming back via its drivers on the host PC using the Dscope Series 3 software in a closed loop, preventing you from having to use any external signal generation or signal analysis software. So let's look at a simple measurement then, frequency response, and I'm going to do that by applying an analog input signal to a USB audio evaluation board. It's a relatively low cost device that's designed to offer mic input and line output for laptops and portable tablet type devices. So I will be applying an analog input to its inputs here, and I'll analyse the digital output that's returned to the host PC via the USB connection between the evaluation board and the computer. So let me load that test then, and first of all I need to select sound card mode because I'm actually measuring the input, as I say, from this sound card device, and in this case I need to feed it an unbalanced input, and I also need to select the device that I want to measure. Here are all the devices that have digital inputs that are connected to my host PC. It's this one here I want to select, and I also need to connect it to my test system. So I'm just now connecting the analog outputs of my test system to the analog inputs of this Adca D converter device. Okay, that has now been completed, and you'll see straight away that we seem to have some rather excessive distortion in the digital output of this Adca D converter. That's because it's designed to handle microphone level signals, and right now I'm generating a signal at quite a high amplitude for this device. So I need to find my DA lineup once again. So that's now happened automatically behind the scenes, and you can see now I've got significantly lower DA lineup than we had before. Minus 22.16 dBu of analog signal level will give 0 dB FS, 0 dB full scale digital output of this converter device. So having set that up, I can now load my tests, whichever ones I like, in the same manner as I did with my previous measurements, and let's measure frequency response. So this particular test, again, it's a sweep, and it is configured to sweep the generator frequency over a range of 20 kHz to 20 Hz. So this is an analog sweep starting at 20 kHz, ending at 20 Hz, and we're going to measure the digital output from this Adca D converter via its USB connection to the host PC. So we're talking to the device drivers rather than to an AES or I2S interface. Okay, so I can now run my tests, and we will see the result as this test progresses. You can see the FFT data updating as this sweep runs, and the frequency response is being plotted on the screen as we talk. And as with all the previous tests, I can now, having run that measurement, hit the Create Report button, and there is the frequency response of that particular device, measured in units of dBr relative to the 1 kHz signal amplitude. That reference point was automatically set up for us behind the scenes before I ran the test. Okay, and I have one final measurement that I'm going to take you through now, and I want to consider the noise performance of this device. And again, I have a survey to involve you, the audience, and again, if you're using a PC, you will see a survey question appear on your screen, and the question I'm asking you is, how would you measure the dynamic range of an audio Adca D converter? So your options are, firstly, you could measure the signal, then mute your test system and measure the noise. You could inject a minus 60 dB FS signal and measure the output with a notch filter. You could run an amplitude linearity sweep from 0 dB full scale right down to minus 140 dB relative to full scale. You could use an FFT in conjunction with a 0 dB full scale signal. Perhaps you think none of the above. If you could just check all of the ones that you think would be appropriate for measuring the dynamic range of our Adca D converter, I would be most grateful. And when you have had a few moments to consider those answers and to complete them, then we will take a look at how you have responded. So, as I said with all the previous surveys, this is anonymous. We just want to measure the statistical response of our audience today rather than singling out any individual answers. So bear that in mind as you participate, and I will stop that survey running in a couple of seconds so that we can take a look at how you responded, which we will now do. Okay, so the first response here, measure the signal, then mute the system and measure the noise. That's how we might have measured dynamic range in the past, but it's not how we generally recommend measuring it today, and I'll explain why in just a moment. Some of you have said that you could run an amplitude linearity sweep starting at 0 dB full scale and ending up at minus 140 dB relative to full scale. That, provided you set it up appropriately, is potentially one means of measuring the dynamic range. However, it does rely on a sweep, which is relatively time consuming, and we can measure dynamic range much more quickly than using that sweep. Some of you have said you could use an FFT in conjunction with a 0 dBFS signal. That is a possible method that you could employ, but there are some health warnings that come with that particular method. One of them is that it's not very easy to establish noise directly from an FFT result, so you need something with some more sophisticated processing capabilities to be able to integrate over a wide range of frequencies and return an RMS value for your noise floor. The other issue is that when you're dealing with very high-end A to D and D to A converters, you may be potentially running close to the limits of your measurement system in terms of its ability to measure noise in the presence of signal. So what we really want to do is to use the measurement system on a very sensitive input range, i.e. not with full-scale signal running through your A to D converter. So in fact, the measurement method that we use for dynamic range, the measurement standard specified in the AES 17 recommendations, is to use a 60 dB below full-scale signal and measure the output with a notch filter. And let's just explain that before we do the measurement. So dynamic range historically was traditionally measured by, first of all, measuring our signal and then measuring noise with the generator off. Now that worked fine in the world of analog measurements, but with digital audio devices and converters, it's quite possible that the device may mute when it detects no input signal, and that will give you an artificially low value for noise, and so it will give you an unrealistic dynamic range measurement. So as I said, the AES 17 recommendation suggests using a 60 dB below full scale audio signal, and then you apply a notch filter to the output. So as we saw earlier, it's very useful to be able to define our DA lineup, so we can very simply punch in an analog signal amplitude at 60 dB below full scale and then measure the output. So what happens then? Well, here's a measurement, an FFT, of an A to D converter running at a signal amplitude of 0 dB full scale at its input. And we can see the noise here, we can see some distortion products, possibly some intermodulation artifacts as well. If we reduce the signal level by 60 dB, then all of that distortion energy also gets reduced by 60 dB. The noise probably doesn't, and if I re-measure that device, just measuring it with an input signal of 60 dB below full scale, then what we tend to see here is that we get a nice clean noise floor, because all the distortion products are now below the noise floor, and we can simply apply a notch filter to remove that tone and give us a measure of the noise floor in the presence of a low level signal so that the converter doesn't mute. So finally then, I'll run through a demonstration of dynamic range according to the AES 17 recommendations, and I'm using exactly the same USB audio evaluation board as I was before. I'll jump into my test system here and load the dynamic range measurement. So you'll see, if we go to the settings page, that the generator has been set up to give us an analog signal 60 dB below the full scale input amplitude, and you can see here in the FFT that yes, we've got 60 dB below full scale in the digital measurement, and our dynamic range is shown here as about 74.5 dB, which doesn't seem all that great, but bear in mind that this is a low-cost device and it's a microphone preamplifier that has a lot of gain. For now, what I'd like to do is just take you through a recap of what we have talked about so far. So we've seen that measuring A to D converters can be quite a complex and time-consuming affair, and it does potentially require quite a detailed understanding of the measurement theory in order to come up with meaningful, consistent measurements of your A to D converters. So in order to take that time out of the process, we have introduced this brand new A to D converter measuring suite that's designed to make life a lot simpler, more straightforward and faster when it comes to benchtop analysis of your A to D converters. We've seen it's very simple to use. We just simply click on a few buttons, select a measurement result from a drop list, hit the run button, create a report if we want to, and all of the hard work is taken care of for you behind the scenes. And importantly, as I mentioned earlier, it's highly programmable, so that if we want to modify these tests in any way, and I've shown you a couple of very basic examples as we've gone through, you can make those changes to suit your needs, whatever they be. This application runs on existing D-Scope Series 3 measurement systems, so you can download this application from our website and run it on your analog and digital measurement system if you already have a D-Scope, as a number of you do. And as we have seen, this is good not only for measuring A to D converters with hardware outputs on AES EBU or I2S or other serial data connections, but also on PC audio devices where you want to measure your device using the digital output that is being sent to the computer at driver level. So a few references for you. I will ask my colleague Graham Boswell, who's co-moderating this session, to paste these links into the NetViewer chat window for you so you don't have to write these down. If you want to look into more of the design side of A to D and D to A converters, then Ian Dennis's AES paper is available at the following location on our website. If you want to read into more of the background theory on, in particular, the diagnosis and solution of jitter-related problems in digital audio interfaces, this is a link to the seminal paper by Julian Dunn and Ian Dennis of Prism Sound, looking at these jitter-related problems. There's another Prism Sound paper here. This is the paper where we derived the graphs of the maximum permissible sampling jitter to ensure inaudibility of jitter modulation components. And there's another paper here that illustrates the importance of a stable reference voltage in your converter designs, and I won't spoil the mystery here, but the mystery was that there were instances in the past where we had reports of CDs that were numerically identical that sounded different to one another, and I'll leave that to you to investigate if you want to learn more about how that could possibly have been. Finally then, a couple of additional AES documents. This is the AES 3 standard that Ian Dennis, our technical director, co-authored. This is available from the AES website, as is the AES 17 recommendations for digital audio measurements. Things we've not had time to go through today in detail. Well, as I said earlier, this is part 2 of a 2-part series. We covered D2A converter measurements in a separate webinar, and we looked at some of the other measurements that we didn't have time to cover today in the A to D session. FFT analysis has been used fairly extensively throughout today's presentation, but it's something that you may want to learn more about in more detail. And testing sound cards and professional audio interfaces. This and a wide range of other webinar topics, past webinar events, is available for download on the Prism Sound website, prismsound.com/webinars. So if you enjoyed today's session, got something out of it, then by all means, please feel free to access our website and download any of our wide range of additional educational webinars that you may find interesting. So thank you all very much for your time and attention during today's presentation. I hope you found the session useful and informative, and look forward to welcoming you back to another Prism Sound Wednesday webinar in the not too distant future. So thank you to Graham, my co-moderator. Thanks again to you, the audience, and it's goodbye from us for now. Goodbye.